John Flamsteed was not a man to be trifled with. Fiercely intelligent and possessing an attention to detail and precision, he was not the sort of man who did any job halfway. He was the kind of man who might have subscribed to something my mother used to say to me when I wasn't as fastidious in doing my chores as she wanted. If you're going to do a job, do it right. For John Flamsteed, doing it right meant rigorous attention to detail and a nearly obsessive passion for accuracy. Like Newton, Flamsteed had been born in a small country village. His was Denby in Derbyshire, and like Newton, he displayed an intellect that set him apart. Raised in a reasonably well-to-do family of malters, the young Flamsteed excelled in school, learning Latin, history, and some science before being admitted to Jesus College, Cambridge in 1662. Unfortunately, a bout of ill health delayed his attendance, but he didn't waste the time. Instead, he worked in the family business and so learned the fundamentals of mathematics, and in September of that year observed a partial solar eclipse that fanned a burgeoning interest in astronomy. Over the next 8 or so years, he learned everything he could about the subject, often under the tutelage of William Litchford, and in 1665 wrote his first paper on astronomy, a short discussion of his design, construction, and use of an astronomer's quadrant and the observations he made with it to establish the latitude of Denby. In time and with this experience, he did finally enroll in Cambridge as an undergraduate in 1670, and it is likely that while a student he would have heard some of Newton's earliest lectures as Lucasian chair. While he would never take up residence at the school itself, Flamsteed was enrolled in 1674, and while I've not been able to determine if he graduated for sure, it seems likely that he did, as he was ordained a deacon in the Church of England that same year. During these years, his work in astronomy continued, and while he had planned to return to Derbyshire to take up a post in the church there, the work that he did caught the attention of a very important figure, one Jonas Moore, who realized that Flamsteed had the tools and the means to help with a project that was being conceived in London. Moore was the Surveyor General of the Ordnance and had made an offer to the British Crown to fund the construction of an observatory. England, as a growing maritime power, had a problem, one they shared with their most able competitors across the English Channel, the Dutch. While determining the latitude of a ship was relatively easy, longitude was another matter. As we've discussed in a few previous episodes, it was understood that the best way to solve the problem would be to keep good track of the time at some reference point while traveling, and then compare that to the local time and use the fact that the further west the observing position is, the later the sun will cross the meridian in the time frame of the reference position. The problem was that there were no good human clocks that were reliable at sea. While Huygens pendulum clocks could keep good time on land, the vicissitudes of ocean travel rendered them useless. Instead, the idea was to use the oldest clock in human memory, that of the sky, and the motions of the bodies therein. There were a few different schemes devised to do this, some using the moons of Jupiter, as Galileo had suggested, others working from the positions of the Earth's moon. No matter the strategy, it was understood that exceedingly precise observations would be needed in order to create the various heavenly charts and tables navigators could use to compare their local measurements to and then make calculations. Making these observations would require a centralized facility and a person to do the work. With this in mind, Moore brought Flamsteed to London in 1674, where the man from Denby was made an assistant to a project to consider a specific method for determining longitude. While the proposal was soon deemed unworkable, Flamsteed impressed the men on the commission appointed to study the idea, including Robert Hooke and Christopher Wren. I wish I could tell you that the Royal Observatory had been established out of reasons of scientific curiosity, but as often is the case with such endeavors, it seems that Charles II had other motives. Apart from the issues of promoting commerce and increasing national security, Charles seems to have had a case of keeping up with the Bourbons. Louis XIV had established an observatory in Paris and had recruited one of the best astronomers of the day, the Italian Domenico Cassini, to run it. For it to seem as if the British had fallen behind the hated French was a bad look, and so it appears that Charles II allowed himself to be persuaded to create an observatory if a suitable sponsor could be found. After a few years of starts and stops, the British Crown accepted More's offer to fund an observatory on a small hill across the Thames River opposite London in the town of Greenwich. However, given England's limited tax base, the meager financial resources necessitated that the person to equip and run the observatory would have to be homegrown, as Charles was not interested in headhunting the astronomers of Europe as Louis had. Charles needed a prestige observatory, not a prestige astronomer. Fortunately, though, he did get that. More, of course, knowing of Flamsteed's reputation for exacting measurement and a nearly obsessive attention to detail, understood that he was the ideal candidate for the job. It was for this reason that More had initially recruited him from Cambridge in the first place. In 1675, the king established the Royal Observatory, and John Flamsteed was made its first astronomer royal. In the year that Issac Newton was meeting with Robert Boyle to discuss alchemy and writing letters to the Royal Society on the nature of light and matter, Flamsteed was making the initial purchases of equipment that would form the heart of an institution that would prove instrumental to Newton's work just a few years later. Then he would be a somewhat unwilling participant in the revolution to come, even as he helped create it, would anger Britain's chief astronomer for much of his life, and it would cause him to regret writing those first letters to the Hermetic philosopher of Cambridge, whose lectures he had attended as a student. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 27.4, Supplemental. Issac Newton, Principia. The letter Issac Newton received from Robert Hooke near the end of 1679 was, in many ways, the thing that changed everything. It came at the right time, a time when, nearing his 37th birthday, Newton was likely taking stock of his life and accomplishments. His mother's death, combined with those of his former sponsor Barrow and Oldenburg in London, as well as the approach of middle age, may have had him contemplating his own mortality, and a recent fire in his alchemical laboratory had set back his work on that front. While the main reason for the letter, a request for recent work to publish, had had little effect, as Newton claimed to have left work in natural philosophy far behind, it was the seemingly innocuous question at its end that re-engaged the reclusive genius with problems that had solutions. As we've discussed in a previous episode, Hooke's letter was an attempt to get Newton to reopen their very strained relationship, and maybe also send him something to be discussed at a meeting of the Royal Society. While Newton declined to engage in public philosophical discussion, still frustrated by the contentious things that happened and had occurred around his papers on light and optics, he did propose a sort of toy problem about what the motion of an object dropped from a high tower might be. First from the top of the tower to the surface of the earth, but also, in a sort of thought experiment, what would happen if the ball was allowed to pass through the body of the earth and continue towards its center. It was a sort of question Newton had abandoned a decade or more earlier. However, it was one that Hooke and other members of the Royal Society were very curious about, as they were attempting to figure out both planetary motion and the nature of falling bodies. As we've already discussed the specifics of each man's ideas on an earlier episode, let's focus on why the brief exchange of letters is more than a just passing historical interest. For our purposes, the short correspondence was important for three reasons. First, it shows that while Newton has some of the pieces that would become part of his grand synthesis some 8 years later, it's pretty clear that the ideas that he has are still pretty fragmentary and in some cases fairly far off the mark. Second, it is in one of these letters that Hooke puts in writing his supposition that the force that is responsible for planetary motion becomes weaker as the inverse of the square of the distance between the large central object, say the Earth, and the thing orbiting it, i.e. the Moon. If you will recall, Newton had more or less deduced this by comparing the accelerated motion of a falling body to that of the Moon back in 1665-1666 when he was at home in Woolsthorpe. But his calculation then had been both fairly rough and based on the idea of there being both inward or centripetal and outward or centrifugal balancing forces that allowed the object to move in a circle. Finally, in the letters explaining their ideas and justifications, neither man made any reference to the mechanical philosophy of Descartes. Gone from their discussion were the mentions of vortices filling all space and the impression of contact forces from one vortex to the next as a way of transmitting force and generating motion. Whether this was due to the influence of Boyle's more traditional atomic theory on the scientific community of Britain, or a recognition that Descartes' explanation could not be used to create mathematical descriptions or models, is somewhat unclear from my research, but the letters very clearly mark a clear break in Newton's thinking from those ideas. Of course, things are never quite so simple when it comes to Hooke and Newton. Hooke, it seems, continued to nurse a grudge against Newton, perhaps justifiably. Thus, even though he had promised in the first letter of the correspondence to keep any discussions private and out of the intellectual discourse, something that allowed Newton to be significantly more speculative in his ideas than he would otherwise have been, Hooke went ahead and read Newton's problem and analysis aloud at a meeting of the Royal Society as if it were a serious submission for consideration. He then proceeded to contradict Newton's speculative ideas, thus aggravating the other man tremendously. When Newton responded to Hooke's reply with an acknowledgment of his error and additional speculation, Hooke once again seized on the opportunity to point out those places where Newton's reasoning was incorrect. This was the last straw for Newton, and once again he descended into silence. At this point, it's probably safe to say that Newton despised, and perhaps even hated Hooke with an enmity formerly reserved only for his long-dead stepfather. Nevertheless, the exchange had forced Newton into unfamiliar territory. It called into question a number of his ideas first put down and written into his 1666 waste book, and thus it impelled him to reconsider his assumptions made there. Hooke had made him rethink and redefine the problem in a way he had not before. Newton might retreat back into his physical and philosophical isolation, but it wasn't the same person who did so. Newton was thinking about old ideas made new through the process of rubbing up against the ideas of Hooke. The correspondence had helped the two men express what they held in common when looking at the motion, and to make distinct what each thought different than the other. It also fueled Newton's desire to show that Hooke was wrong in his ideas, something he began to consider showing in earnest. Now, had the Hooke correspondence been the only thing that happened, it is possible that Newton might have toyed with the ideas for a time and then once again allowed them to sort of slip from the forefront of his thought. However, celestial events conspired to keep his mind focused on the heavens and their motions. On November 14th of 1680, a comet was first observed by the Prussian astronomer Gottfried Kirch. As an interesting historical footnote, this comet is the first one ever observed with a telescope. The comet, now known as Kirch's Comet or Newton's Comet, grew somewhat brighter throughout the month, but remained beneath the notice of many observers. As it moved closer to the sun, it disappeared from view, but then, a few weeks later, another comet appeared in the heavens on the opposite side of the sun, even brighter than the first had been, so bright in fact that it was reportedly visible during daytime. It was something that attracted the attention of astronomers throughout Europe and across the Atlantic, where a group of colonists, struggling to survive in an unfamiliar place, were frightened by the omen its long, bright tail presented. The Puritan minister, Increase Mather, was so concerned that he delivered a sermon to his flock titled, Heaven's Alarm to the World, to warn of God's displeasure and exhort his congregation to repent of their unending wickedness. This second comet was observed from December 29th until March 19th, when it became too faint to see, even with telescopic aid. Almost immediately, though, a debate sprung up regarding these two events. Some astronomers and natural philosophers claimed that these had been two different comets. The reason for this was that many assumed that comets traveled in straight lines, or mostly straight lines, through the celestial realm. This had been the opinion of both Tycho and Kepler, who, lacking the long and exhaustive records kept by Chinese astronomers, understood such events to be singular in occurrence. A comet flew past the Earth, traveling through either Ptolemy's or Copernicus' non-existent crystalline spheres, never to return. Others, however, said that for two comets to have appeared in the way they did was unlikely, and that what had been observed was in fact a single comet that had first traveled towards the Sun and then had reversed direction and traveled away. Among these was the astronomer royal, John Flamsteed. Flamsteed had missed the first comet, but was quickly alerted to it through correspondence. In looking at the observations made of the first appearance by others, he began to wonder if comets might instead travel around the Sun in the same way planets, but in a more elongated orbit. If this was the case, he believed that the comet would emerge from the glare of the Sun near the planet Mercury, and thus he turned his instruments at the Royal Observatory there in late December and was rewarded to be one of the first to see the second appearance of the comet, or at least that's what he thought, in contradiction to the prevailing wisdom of the time. As he accumulated data and began to formulate an explanation of his hypothesis, he decided to reach out to Newton through a common associate, one James Crompton. When that proved unsuccessful, he wrote Newton directly with his speculations regarding the nature of the comet and asking for the Cambridge Fellow's opinion on the matter. Still receiving no word, Flamsteed tried one more time a month later. This second letter contained more than just a hypothesis, but a fuller explanation of the reasoning behind the single comet idea. What Flamsteed thought was that the comet had traveled towards the Sun, attracted by a magnetic force similar to that Kepler had put forward. The Sun, however, like all known magnets, had two poles. As the comet had approached, the Sun had rotated its attractive pole away from the comet and its repulsive one towards it. Recall that Galileo, among others, had shown that the Sun did rotate on its axis through the observations of sunspots. This change in magnetic pole, and thus the magnetic vortex around the Sun, had thus stopped the comet in the space between the Sun and the Earth, and then pushed it away to once again be observed, this time traveling in the opposite direction across the sky. In retrospect, while Flamsteed was certainly wrong in his idea, it's a somewhat ingenious way to explain what had been seen that did use the work of both Gilbert and then Kepler and Galileo in a really unique way. This, of course, finally roused Newton to take up a pen and respond. He too had been observing the second appearance with a telescope on the grounds of Trinity College, though not with quite the precision of Flamsteed, who possessed better instruments and a greater obsession with accuracy. He rejected Flamsteed's ideas on the grounds that Gilbert had shown that any magnetized object that was heated to high temperatures would lose its magnetic properties. Thus, the Sun, being very hot, wouldn't have had any. Newton then went on to write that his observations seemed to rule out the two events being one object. If Flamsteed's ideas were true, he said, the motions of the comet through the sky, first speeding up, then slowing down, then speeding up again, and doing so in such a short time, went against what was understood about planetary motions. However, what is crucial here is that Newton diagrammed an alternative to Flamsteed's idea that would be fundamentally important to what would transpire in the years ahead. What Newton suggested as an alternative was that if the Sun exerted an attractive force on the comet, it was possible that the comet could have passed by the Earth, swung around the back side of the Sun, pulled by the Sun's attractive force, and then traveled away from the Sun in a path that was well described mathematically. In the letter he wrote, quote, "I can easily allow an attractive power in the Sun, whereby the planets are kept in their courses about him from going away in tangent lines." End quote. Now, this is a really important place to pause and consider what Newton's done here. Today, we all have the idea that gravity, whatever we might think it is, works the same everywhere in the universe. In the modern mind, it is a universal thing. At the time of Newton, though, Still working to loose the shackles of Aristotelian thinking, the idea of gravity being something that happened beyond the surface of the Earth was something very, very new. Remember, Kepler thought it was magnetism or something like it that worked on celestial scales. Men like Descartes, Hooke, Huygens, and even Newton had extended some of the ideas of terrestrial physics as far out as the moon, but there wasn't a lot of thinking to suggest that such forces extended beyond that point or even existed in the celestial realm. For Newton to suggest that an attractive force from the sun acted on the comet, much like he thought an attractive force from the Earth acted on the moon, was a huge intellectual step. It is very difficult to overemphasize this point. Newton is proposing an entirely new mechanism for what the cause of motion for celestial objects might be. Another thing to recognize here is that in his explanation, Newton seems to have dropped the combination of both centrifugal and centripetal forces. The outwardly directed centrifugal force has been completely abandoned, indicating Newton's acceptance of Descartes' ideas regarding the natural motion of objects having to be in straight lines, something we now call the law of inertia. Finally, it is pretty clear from the quote we just heard, and other things that he wrote in response, that Newton has begun to think of these problems in terms of his fluxional calculus, something we'll return to shortly. What happens after this is a bit hard to piece together, because Newton once again kind of goes silent in terms of public communication. From later events, however, it seems reasonable to conclude that Newton, intrigued by the motion of the comet and perhaps still thinking about his correspondence with Hooke a year earlier, began to noodle around with some of the ideas the two had discussed, as well as with his old notes from the plague years. As he started to pull on various threads, he began to see a more coherent picture emerge, something that he alone had the tools to create. This was spurred on by the appearance of yet another bright comet in 1682 that allowed him to test some of his ideas. At some point during those years between 1681 and 1684, he produced something between what we might think of as a sketch and a study that showed that if one assumed an attractive force that gets weaker the further away something is from a massive central object in a very exact way, i.e., that the strength of the force decreases as the inverse of the square of the distance, one could show that the paths of objects around the central mass would be ellipses. This, of course, was a tremendously important step, and, as was so often the case with Newton, he kept it to himself. Were it not for a talented and inquisitive young assistant of Flamsteed's, it might never have seen the light of day. As Newton toiled away in isolation, the most brilliant minds of London continued to worry at the problem of celestial motion. The nucleus of this group was Hooke's coffee-house gathering of himself, Christopher Wren, and a young, well-to-do astronomer, natural philosopher, and mathematician by the name of Edmund Halley. Halley had come to London by way of his studies at Oxford, and had made a name for himself by taking a pendulum to the top of the tallest mountain on the island of St. Helena and measuring the period of oscillation. He had found it to be just a bit slower, suggesting that the attraction of the Earth might be just a little bit smaller at higher elevations. While there, he had also carried out an extensive program of nightly observations of the sky that both extended navigational star charts further south that had been previously available, and that allowed him to make corrections to Tycho Brahe's star charts, something that earned him both a part-time position at Flamsteed's Royal Observatory and election to the Royal Society. As I hope to do a bit of a supplemental episode on Halley, let me leave any other biographical details about his life and scientific work to that. The three men, along with a variety of others who would join their discussions from time to time, made it a regular habit to discuss the scientific issues of the day when they gathered to drink the newly popular beverage not long arrived from the Middle East. One of the topics they returned to again and again was that of planetary motion and the motion of comets. Hooke had, in the years since his correspondence with Newton, held forth that there was an attractive force from the sun that he believed varied as the inverse of the square of the distance. This was supported, no doubt, by the report of the letter from Newton to Flamsteed that would have been made by Halley. Halley shared that he had been able to prove that if the inverse square law of the attraction were true, then Kepler's third law of planetary motion could be derived from it. This was something, of course, that Newton had done back in 1666, but nobody knew that. What none of the men could do was figure out how to get Kepler's other two laws from that assumption. Hooke had bragged that he had worked it all out, but that he was keeping it secret for a time being, so that as more people failed to come forward with a solution, his final triumph when he revealed his mathematics would be all the greater. By the way, this is just typical Hooke right here. We now know, and his friends at the time, by the way, strongly suspected this, that he didn't actually have anything, but was rather positioning himself to be able to take credit for the ideas of someone else when the time came. In 1677, Hooke had taken over as Secretary of the Royal Society after Oldenburg's death, and he had proceeded to alienate enough people that the Society was now in financial difficulty and was struggling to find enough material of note to publish in the Philosophical Transactions on a regular basis. Very few natural philosophers, it seems, wanted to publish in the journal, only to have the Secretary say something like, "Well, as you can see, this is a very nice piece of work, and its author should be commended. But I might point out that I had the same idea 2 years back, and I'm very disappointed that I have not been credited with its discovery." End quote. We actually don't have a record that, Hooke ever said anything quite like that, but that was the tenor of the comments that he tended to make, not infrequently. Anyway, Wren sort of had enough of all the bragging and lack of progress, and so in 1684 he laid down a wager to get people, meaning of course Hooke, to either put up or shut up. The amount was some 40 shillings, or about $500 in today's money, enough to spur interest among the more mathematically inclined members of London's intelligentsia, and maybe to get Hooke to come forward with whatever he had. However, by the end of the 2-month deadline that the work had to be produced by to collect on the bet, no one had produced any sort of a proof. So in August of that year, Edmund Halley decided to leave London and travel to Cambridge to chat up Newton about the idea. The letter to Flamsteed had been full of tantalizing hints, and Halley thought there might be more that Newton had done. One of the great mysteries of this story is how Halley was able to get Newton to open up. From an entry in his personal notes, we know that Newton had met Halley once back in 1682, and so this wasn't exactly a cold call, but it's not like the two men were close in any way. However, Halley knew Newton well enough to recognize that if he traveled to meet the Cambridge fellow in person, he wouldn't be turned away, if for no other reason than the rules of polite society forbade it. Thus, when the young man asked to see Newton, the recluse agreed to greet him. After some introductory pleasantries, Halley asked directly if Newton had any ideas regarding what sorts of orbits planets would make if the sun created an inverse square attractive force. Surprisingly, rather than demurring, Newton expressed that the orbit would be an ellipse, just as Kepler had derived from Tycho's observations. Halley then asked Newton how he knew this, and Newton simply responded that he had worked out the mathematics some time before. When Halley asked to see the proof, Newton made a bit of a show looking around his rather cluttered chambers, and then said that he couldn't quite put his hands on it at the moment, and that would it be all right if he sent it along at a later date. Halley, both excited and disappointed, agreed to the arrangement, but one has to wonder if he questioned whether Newton was just pulling another stunt, kind of like Hooke had done. The truth was that Newton had known exactly where the work was. He also known that it had been done as a sketch rather than as a precise mathematical proof. In other words, it wasn't rigorous enough to be shared with an intellectual community. He needed to check his work to make sure that if Halley pulled the same stunt Hooke had 4 years earlier, he wouldn't be embarrassed by it. Over the next few months, he set out to create a formal document founded on mathematical axioms and physical definitions. He did actually find a mistake in his earlier sketch, and so he corrected that, and he also tightened up his ideas on motion that had first been written in 1666-1667. and then more completely developed after the correspondences with Hooke and Flamsteed. When the document arrived at Halley's residence in London, it was not merely a straightforward treatment of the simple question Halley had posed. Instead, in its 9 pages, the document, titled De Motu Corporum in Gyrum, or On the Motion of Bodies and Revolution, Newton developed the proof from a first definition of a quantity of matter that led to the idea of mass, and a quantity of motion that led to the idea of momentum, something similar to the older notion of impetus. To this was added the concept of force as that which changed the quality of motion, and then the specific case of a centripetal or centrally directed force was considered. Once these ideas were established, Newton was able to show that if that centrally directed force was inversely proportional to the square of the distance, then not only would an ellipse be the result, but that all of the conic sections could arise as possible orbits of an object around the sun. The work was a bolt of lightning into the philosophical community of London, and Halley's single copy of the work was the thing to see among anyone in the know. As an example of just how in demand the manuscript was, Flamsteed complained, somewhat bitterly I might add, that he would never get to see it for himself until after Hooke and his circle had had their time with it. Halley, for his part, tried to remedy the situation by asking Newton to publish the work formally and perhaps, maybe, could you expand it a little bit? What Halley didn't know at the time was that in writing the short manuscript, Newton had seen not only a solution to a specific problem, but instead had glimpsed that it was part of a much larger and more comprehensive reimagining of the totality of motion. He had begun to write not just about the motion of the planets, but also about the motions of all things in the universe. A universe, by the way, Newton was now fundamentally restructuring. As his work progressed, he began to need data to better understand the full variety of motion of things in the heavens, and so he wrote to Flamsteed to ask for his cometary observations. The Astronomer Royal guessed that Newton was looking to expand the manuscript to show that his supposition that comets moved in planetary-like orbits was correct. But then came a request for the observations of the moons of Jupiter. Then for tables of tides. Soon Flamsteed was confused as to what Newton was getting at. He didn't see that Newton was constructing a comprehensive theory of all motion. In this work, all of Newton's other intellectual pursuits were left to languish. For the first time in nearly 20 years, the alchemical furnaces were allowed to go cold, and there were no theological examinations produced and then hidden away. Light was no longer shown through lenses or reflected off mirrors. The heavens, so much the subject of parts of the work, now went unobserved as Newton became completely absorbed in the work he was creating. Thousands of pieces of paper, notebooks, and lying loose were collected, examined, revised, and then transcended. Rarely did he leave his chambers, and he often wrote standing up. He wrote with a passion and an obsession that he had not seen since the plague years. For the next 2 years, Newton calculated and wrote, and in 1686, the first pages of a brand new work were delivered to Halley as the first book of what was to be titled The Mathematical Principles of Natural Philosophy. Somehow, in all of this, Halley had managed to do that thing which no other person had ever done: get Newton to publish his ideas for all the world to see and work through. In the past, we have noted that there are cases where the great work of one man was in fact made known through the efforts of another. It was Regiomontanus who had seen that the full work of Puribach had been published. We have mentioned the oft-held belief, no Rheticus, no Copernicus. Now, again, one has to wonder if Newton's Principia would have ever been written, much less published, had not Halley somehow managed to draw the reclusive scholar from his self-imposed exile and focus all of his vast intellectual power on this one problem. And it should be noted that this question goes beyond one mere aspect of the work's publication. Not only did Halley draw Newton forth, he worked endlessly to soothe the older man's sensitive ego and touchiness, keeping him on the task of not only creating the framework, but writing it up for publication, even when Hooke threatened to derail the entire project, something we'll discuss in a moment. Beyond this, like Rheticus had done with Copernicus's work, Halley underwrote the entire cost of the first edition of the book's publication. While the Royal Society had agreed to sponsor the printing, it did so only under the condition that Halley assume all of the financial risks and liabilities. So it was that Halley oversaw every aspect of the technical details of getting the manuscript pages and diagrams through the printing process mostly error-free and as Newton had intended. The whole thing would consume 2 years of the younger man's life, but as he read the work being sent to him, Halley became not just an admirer of Newton's, but a true believer in the new conceptualization of physics being put forward. More than anyone, maybe even more than Newton himself, Halley understood the truly revolutionary nature of what was in the Principia, and he was determined to see it shared with the world, whatever it took. The publication of the full Principia almost ended up being incomplete for 2 reasons. The first was that Book 3 turned out to be a lot more complicated than Newton initially expected it to be. The calculations, some of which required the full set of tools offered by Newton's calculus, were subtle and tricky, and it took Newton a good bit of time to get through them. The other reason, though, was that Robert Hooke just couldn't help but inject himself into the project. When Book 1 had been delivered, it was, as one might expect, given a good once-over by the Royal Society, whose name was going on the thing, to make sure that there wasn't anything tremendously controversial in it. As one of the leading figures in the society, Hooke would have had occasion to see the early proofs, even if he hadn't been meeting with Halley and Wren on a regular basis. What would have struck most of the early reviewers, if they can be called that, would have been just how impenetrable the text actually was, how hard it was to actually read. Most of them wouldn't have been able to follow it beyond the initial set of proofs, as we'll discuss in a few minutes. What would have also stood out, however, especially to Hooke, was the fact that Newton included a section on the motion of objects subject to an inverse square attractive force. He would have also have noticed that in this section, there was no mention of him in any way. While the work was certainly all theoretical, and thus not specifically applied to the solar system, Hooke expressed his view that in subsequent portions of the book, he expected that Newton would acknowledge that Hooke had actually given him the idea of the inverse square laws applying to celestial motion. In other words, Hooke wanted credit for Newton's discovery, first put forth in the 9-page manuscript, and now being expanded upon in this, the Principia. As we have seen, there is likely some validity in Hooke's request, as Newton himself would later tell Halley that Hooke's letters had once again gotten him to think along those lines again. But what Hooke was asking was far too much. Hooke had had an idea, and not a particularly original one at that. It turns out that Wren could have made the claim that he had had similar ideas earlier than Hooke had, as could men like Huygens. What neither he nor any other person had done was take what was an interesting and clever notion and done the hard mathematical work to show that it was, in fact, true. Only Newton had done this. When Halley communicated Hooke's request to Newton, that was nearly the end of the project. Now, Book 2 was too far along to keep from the printer, but Newton threatened to withhold Book 3 from publication, as he knew that this was where he would be applying the mathematical formalism developed in Book 1 to the actual solar system. He also went through Book 2, and he took out Hooke's name in every place that he possibly could. Prior to this dust-up, he had planned to acknowledge Hooke's work in several places with respect to things like pendula and clocks, but now all of those mentions were removed or replaced with other names. Newton had had it with the endless disputations he saw in natural philosophy in general, and with Hooke in particular, and he was of a mind to end the Principia without the final applications to celestial motion. It was only after a good bit of placating and reasoning that Halley was able to convince Newton that if he didn't publish the work, someone else would figure out how to apply the ideas in Book 1 and take credit for what was, rightly, Newton's discovery. Newton thus mollified and motivated, finished book 3, added a preface, and got the whole thing into Halley's hands to be printed and published. In 1687, the full Principia came off the printing press and into the world at large. It was a work of monumental importance and almost completely incomprehensible to nearly everyone who came across it. There are a couple of reasons for this. First, after the dust-up over the thing with Hooke, Newton went back and made the math, especially in Book 3, harder to follow. It's not that any of the math is wrong or that every step wasn't clearly thought out, but rather that he tended to use more obscure notations and terminology in many cases, and would not always spell out every single step in his thinking. Second, the entire mathematical framework for the book is geometric, but not what might be thought of as standard, common geometry. A question arises here as to why Newton didn't use calculus in many of the places where he could have. One explanation I've read is that most of his readers wouldn't have been able to understand, much less follow the calculus, and so it was not used for that reason. Several historians of science, however, have made a good case that Newton never seems to have used calculus in developing his ideas, even when just writing for himself. It seems that Newton, like Kepler before him, saw geometry as the most perfect mathematical expression, and so he preferred to use that. However, what's really fascinating is that in his geometric proofs, one clearly sees the fingerprints of calculus throughout. In other words, I think the best way to see Newton's mathematical method would be to say that he thought in calculus, but wrote in geometry. His proof structure is the sort of thing one would do if one thought in terms of continuously changing variables, but the writing is in the language of triangles and areas. The result was a book that had proofs that many other mathematicians could follow, but who would then ask themselves, how or why did he even take this approach? How did he know to do that? There's this commonly repeated story of a Cambridge student who, after the Principia had been published and various copies had been distributed around the campus to various faculty members, commented to another student after encountering Newton while out on a walk, quote, "There goes a man that writ a book that neither he nor anyone else understands." End quote. While this is not completely true, it is correct that Newton's audience was limited, and that limitation was by design. He had made the third book more mathematical to, quote, "avoid being baited by little smatterers in mathematics." Obviously here, a dig at Hooke. However, he also wrote in the preface that most natural philosophers could skip a number of the more mathematical sections in order to focus on the results of the work. Even though the book was hard to read, men such as Halley and Huygens worked through the opus and found much there to praise. The final note to be made here is that the one other reason for the opaqueness of the book was that it was basically written from beginning to end with very little editing. Newton was rushing to get the work out, and so there wasn't always a lot of thought given to organizing things for the full ease of understanding. Newton notes the shortcoming in the preface, and he asks his readers for their forbearance on the matter. When the second edition is released some 25 years later, Newton will have done much work with the help of men like Samuel Clarke to make the flow of topics more understandable and accessible. So, what is the structure of the Principia? The work begins with a preface or introduction where Newton defines matter and the idea of mass, and then lays out his three famous laws of motion centered around the idea of momentum, that quantity defined as the product of an object's mass and its velocity. He also defines his concepts of absolute space and absolute time, and establishes the idea of the equivalence of reference frames that move with respect to each other with a constant velocity, something now known as an inertial reference frame. It should be noted here, by the way, that most of the first semester of my introductory physics sequence is taken from Newton's ideas just in the preface of this work. He then launches into a series of mathematical proofs in Book 1. These proofs are truly sublime in their elegance and economy. What he's considering is the motion of a theoretical point object with mass under the influence of any number of theoretical applied forces. As I mentioned just a moment ago, these proofs are clearly the product of someone who has mastered the tools needed to think about continuous change as something that takes place in a framework of changing but still absolute time. There were likely only half a dozen people in all of Europe who could have fully appreciated this approach. What is important here is that Book 1 is mostly a mathematical exercise fully leading from axioms to conclusions of that which is, or in abbreviated Latin, QED. In Book 2, these ideas began to be applied to real-world systems. Fluid dynamics is considered, as is the motion of pendulums and projectiles. A significant part of this middle portion is given over to a mathematically rigorous examination of Descartes' mechanical philosophy that is absolutely devastating. Newton banishes vortices by showing that they would not be able to persist over time, and even if they could, they wouldn't be completely unable to produce any real-world motion. Finally, in Book 3, he gave what is called a system of the world. Using proofs built from the ideas of integral calculus, Newton was able to demonstrate that an extended body such as the Earth could be treated as a single-point mass, even if it were irregular in shape and density. Once he does this, all of Newton's mathematical proofs from Book 1 can now be applied to the motion of real objects through real space. And like some sort of wonderful pop-up book, to use an illustration that I read in one of my sources, the whole structure of celestial mechanics just emerges out of that. Herein, he shows that Kepler's heliocentric system with its elliptical orbits can be shown to arise from an attractive inverse square law force that Newton, for the first time, calls gravity. In this, he demonstrates that every mass in the universe exerts an attractive force on every other mass in the universe. From this, he's able to derive the cause of the tides of the ocean. Additionally, he's able to show that the orbit of the moon is caused not only by the gravitational of the Earth, but is also perturbed by the gravitational influence of the sun. In case after case after case, he's able to apply the full force of what he has created to explain what is seen in the universe, and in doing so, he puts an end to all other models of the solar system and establishes as a fact that the Earth is the third rock from the sun, that it rotates on its axis once each day, that it revolves in an elliptical orbit around the sun once every 365.2411 days. Moreover, he derives that due to its rotation, the Earth will not be a perfect sphere, but rather an oblate solid, a sphere that has been squashed a bit at its poles and is a bit bigger around at the equator, something that will be conclusively proved some 140 years later by a French expedition seeking to measure the distance between the Earth's equator and its North Pole to establish a new unit for all humanity called the meter. From this, Newton is able to show that the Earth's precession, that wobbling of its rotational axis like a top, is caused in turn by the gravitational force of the moon and the sun on this equatorial bulge, thus solving a problem that had perplexed humanity for at least 3,000 years. At the end of the third book, Newton wrote an extended commentary on not just the content of the work, but on the process of doing science itself. In this commentary, he put forth 4 propositions. First, he says, quote, "We are to admit no more causes of natural things than such are both true and sufficient." End quote. This, of course, is a restatement of Occam's razor. His second point was, quote, "Therefore, to the same natural effects, we must admit, as far as possible, the same causes." End quote. This is the idea of induction. If we observe or examine a specific phenomenon, and then we see that same phenomenon somewhere else, we should apply whatever general rules we develop to explain the first case to the second. If gravity is said to cause the fall of an apple in an orchard in Lincolnshire, England, it will do the same in an orchard near Ellijay, Georgia, or around Vancouver, Washington. His third statement is, quote, The quantities of bodies that are found to belong to all bodies within reach of our experiments are to be esteemed the universal qualities of all bodies whatsoever." End quote. This is probably the most important of the four statements, as it does away with the Aristotelian distinction between the terrestrial and celestial realms. If gravity is at work on the surface of the Earth, it is also at work between Jupiter and its moons, or between the Sun and comets. Today, this is a fundamental belief of all scientific inquiry. Scientific explanations are thought to work throughout the universe. If hydrogen produces a certain spectrum of light here in a laboratory on Earth, and then if we see that spectrum when we look out into the cosmos, we believe we can make the assumption that it was hydrogen that produced it there, because we understand that the laws of nature work the same in all places. And by the way, this is going to be really important down the road for us just a ways. Finally, Newton concludes by writing, quote, "In experimental philosophy, we are to look upon the propositions collected by general induction from phenomenon as accurately or very nearly true, notwithstanding contrary hypotheses, until such a time as contrary phenomena occur, by which they may be made either more accurate or liable to exceptions." End quote. In other words, this is the process of hypothesis formation and modification. These ideas will go on to form the foundation of scientific inquiry through the age that the Principia will have a hand in birthing. Both the Industrial Revolution and the Enlightenment will be founded on these ideas of inquiry to arrive at natural laws. Now, while Newton's work will initially have only a limited impact, that will slowly change over time. In 1712, when the second edition of the book is printed, and it contains changes to make it more understandable to those without the mathematical tools, it will really begin to take off. Beyond this, however, those who did understand the work would begin to produce what might have been called epitomes in the medieval period. These works would seek to simplify the math and make the conclusions more accessible. As this occurred, more and more people began to master the material and apply it to the world around them. Now, the biggest problem with the Principia was, aside from its impenetrability, was the implications created by Newton's universal law of gravitation. In banishing Descartes' mechanical philosophy, Newton had taken away the mechanism that explained how forces could be transmitted across space. Much like Brahe and Kepler, who discarded the crystalline spheres of Ptolemy and Copernicus that provided a structure for the cosmos, Newton had said that the planets moved through space under the influence of a force that somehow reached across that void. Men like Huygens and later Leibniz accused him of resurrecting the occult forces of the medieval philosophers and thus taking a step backwards, an accusation that was not without validity given the influence Newton's work had from alchemy, along with his underlying belief that there was nothing new to be learned that hadn't already been discovered by the ancient thinkers of the pre-Latin civilizations found in Holy Scripture. Nevertheless, Newton understood what it was that he had done, and so, as a defense, he offered the following words, quote, "I have explained the phenomena of the heavens and of our sea by the force of gravity, but I have not yet assigned a cause to gravity. I have not yet been able to deduce the reasons for these properties of gravity, and I do not feign hypotheses. For whatever is not deduced from the phenomenon must be called a hypothesis, whether metaphysical or physical, or based on occult qualities or mechanical, and have no place in experimental philosophy." End quote. What he is asserting here is that, in the words of author James Gleick, quote, "Gravity was not mechanical, not occult, not a hypothesis. He had proved it by mathematics." End quote. Again, in Newton's own words, quote, "It is enough that gravity really exists and acts according to the laws that we have set forth, and is sufficient to explain all the motions of the heavenly bodies and of our seas." End quote. Those who have listened to our series on the history of the atom will find such thoughts echoed in the arguments surrounding the interpretation of quantum mechanics, where men like Paul Dirac would express that quantum mechanics was correct because it worked, and Richard Feynman would suggest that the best thing to do would be to, quote, shut up and calculate, end quote. In acknowledging this gap of understanding, Newton would do more than just provide a bit of cover for his action at a distance formulation of gravity. He would set forth a research program that those who followed him could take hold of. His framework needed to be applied even further, and so more predictions needed to be made. And that would be the case when Halley, after combing through what historical records there were of cometary sightings and observations, claimed to have found one that was periodic with a 76-year orbit and that would return on a given date, something calculated from an application of Newton's universal law of gravitation. For Newton, the publication of the Principia would bring fame beyond what his papers on light and optics had. While this would be somewhat slow in coming, it would transform his life, just as England was undergoing a transformation of its own from a traditional monarchy to a constitutional one. These changes would propel Newton towards a life outside the confines of Cambridge, one much more in the public eye, filled with both friends and additional disputes, successes and failures, new challenges and opportunities. These, however, we will save for our next episode. As I bring this one to a close, I'd like to say that it's great to be back. It's been a really busy couple of weeks since we last met, at least in this virtual way. Beyond the usual hustle and bustle of the academic year, the scourge that is the academic self-evaluation process, and various bits of committee work, I was able to attend the winter meeting of the American Association of Physics Teachers. It was a great experience, and I got a lot of great ideas about how to improve my teaching and make it more relevant to my students, specifically those students taking physics from the perspective of the life sciences. It was wonderful to renew old acquaintances and make a few new ones, but I have to say it was all just a bit exhausting. These sorts of meetings are often pretty compact in terms of their scheduling, and so I was going from about 8 a.m. to 10 p.m. each day with almost no breaks. The sessions were so full of good information that my hamster wheel of a brain would get going, and I would fill pages in a legal pad with notes with ideas on how to possibly revise various classes that I teach. At the end of the day, it would take a couple of hours to get my mind to settle down. It was a great experience, but this week since then has been pretty weird. On the one hand, I've been churning out curriculum at a record pace for my physics classes as I try to incorporate some of what I've learned as quickly as possible. On the other, I've been slogging through parts of the days, fighting fatigue, and counting the hours until I might be able to sneak in a nap. This weekend has allowed me some much-needed rest, and I am very much enjoying getting back to doing writing for the show. The only real downside with respect to the podcast has been that when the news came out about the TRAPPIST-1 observations, I was too tired and pressed for time to pull something together for it. I'll see if I can try to get one of our impromptu, unscripted episodes together where I explain the science that was done, what was discovered, and what it does and doesn't mean. With any luck, you can look for that midweek or so. After that, we'll continue on the biography of Isaac Newton with 1 or maybe 2 episodes before looking at the life of Edmund Halley. After that, we'll jump back into the narrative more directly to finish out some of the information on the solar system. With all that said, it's great to be back underway, and I hope to be talking to you again very soon. Until next time, full sails on your journey.